Welcome. Dear learner, we are discussing about the radioactivity. In previous lecture, we discussed about the ratio of activity of a daughter to activity of a parent. If we consider the time t is equal to 0, then the ratio of activity of daughter to parent, that is r, is equal to 0. But if we consider the time t is equal to tm, at the time where the activity of a parent is equal to activity of a daughter, then the ratio r is equal to 1. Such type of a equilibrium is known as a ideal equilibrium. So friends, in this lecture we have to see the different types of equilibrium, a radioactive equilibrium. First equilibrium is ideal equilibrium. The equilibrium in which activity of a parent is equal to activity of a daughter, then the equilibrium is ideal equilibrium. Second type of equilibrium is circular equilibrium or permanent equilibrium. The equilibrium in which the parent live extremely long time than the daughter, then the equilibrium is a circular equilibrium. Third type of equilibrium is a transient equilibrium. The equilibrium in which the parent live long time than the daughter, but it is not much more time. Okay, parent live long time than the daughter, but it is not much more time. So we have to see one by one. First equilibrium is a ideal equilibrium. Okay. Ideal equilibrium. We know that the rate of a disintegration of a daughter nuclei or a daughter atom can be represented as dN2 divided by dt. It is equal to lambda 1 n1 minus lambda 2 n2. This equation represents the rate of a disintegration of a daughter atom. The first term represents the formation of a daughter. That is, the parent is disintegrate so that there is a formation of a daughter. And the second term represents the disintegration of a daughter. Or we can say that first term is activity of a parent and second term is activity of a daughter. In case of the ideal equilibrium, the activity of a parent is equal to activity of a daughter. That is lambda 1 n1, it is equal to lambda 2 n2. Okay. And therefore, we can say that dN2 divided by dt, it is equal to 0. That is the rate of disintegration of a daughter nuclei or atom, it is equal to 0. Now, here if we consider the lambda 1 n1 or simply n1 lambda 1 is activity of a parent. So we can represent n1 lambda 1 it is equal to, we know that the according to law of radioactive decay, we can say that N1 it is equal to N0 e raised to minus lambda 1 into T. The radioactive nuclei disintegrate exponentially with the time. And therefore, this equation can be written as lambda 1, N1 is a N0 e raised to minus lambda 1 into T. But the ideal equilibrium is happen only when time t is equal to Tm. And this time Tm can be written as 1 upon lambda 2 minus lambda 1 ln of lambda 2 divided by lambda 1. So this is lambda 2 divided by lambda 1. This represents the time t1 for which the activity of parent is equal to activity of a daughter. Okay, so this is the Tm. Now this equation can be written as N1 lambda 1 it is equal to lambda 1 N0 e raised to minus lambda 1 in bracket 1 upon lambda 2 minus lambda 1 into ln of lambda 2 upon lambda 1. When we put value of Tm, this T is considered as a Tm. Okay, there is a time for which the activity of a parent is equal to activity of a daughter. Now this is a minus a lambda 1 and therefore here is a minus lambda 1. Okay, but due to this minus sign, this term interchange. Okay, and therefore we can write this is lambda 1 N0 e raised to lambda 1 divided by, due to this minus sign, here is a minus lambda 2 plus lambda 1. So plus lambda is taken here. So lambda 1 minus lambda 2 into ln of lambda 2 divided by lambda 1. Okay, can represent like this. Okay, now this term can be also represent as, or we can take this term here and this exponential term goes, that is we can write like this. So lambda 1 N0, okay, ln of lambda 2 lambda 1 into its power lambda 1 upon lambda 1 minus lambda 2. Okay, because this is the exponential term. The opposite or reciprocal of the exponential term is ln. Okay, so we can represent like this. Now we know that half-life period T1 is equal to 0.693 divided by lambda 1. Okay, this is a formula for half-life period for the parent atom. Also, half-life period for the daughter atom can be written as T2 is equal to 0.693 divided by lambda 2. Okay. Now, from this we can say that lambda 1 is equal to 0.693 divided by T1, and lambda 2 it is equal to 0.693 divided by T2. Okay. Now, when we put this value of lambda 1, lambda 2 in this equation, okay, we get N1 lambda 1, it is equal to lambda 1 keep as it is, N0 keep as it is. Now lambda 2 is a 0.693 divided by T2. Okay. And lambda 1 is a 0.693 divided by T1. Okay. 0.693, and so it is cancelled. Okay. So this can be written as ln of 0.693 divided by T2 divided by 0.693 divided by T1. Okay. Its power is again here. Lambda 1 is a 0.693 divided by lambda 1 divided by 0.693, here is a T1. Okay. 0.693 T1 minus 0.693 divided by T2. Okay. Here 0.693, 0.693, 0.693, 0.693. Here we take common and then cancel it. Okay. And therefore, this equation can be written as lambda 1 N0 ln of T1 upon T2. Okay. This equation can be written as T2 upon T1 minus T2. Okay. We can represent like this. Now, this represents the activity of a parent. And we can say that the activity of a parent is equal to activity of a daughter. And such type of equilibrium is known as ideal equilibrium. Okay. When the activity of a parent is equal to activity of a daughter, such type of equilibrium is known as a ideal equilibrium. Okay. So this is related to the ideal equilibrium.